Hello, this is Akos from Enable Training and Consulting. The purpose of this video is to provide an overview of the default 2011 LabVIEW Autonomous Independent VI provided by FRC. We'll start by looking at the front panel of the VI. In this picture, you can see how the robot should be oriented in order for it to follow the line using the code. These controls will set the forward and turning speeds of your robot, and we'll come back to them later. That's about all we can say about the front panel for now, so let's head over to the block diagram. At the beginning of the autonomous mode, the first two digital switches on the driver station will be red to determine which direction the robot will be going. These two binary inputs will be converted into an array, and then into a number ranging from 0 to 3. The number determines the direction the robot will take, which can be either the left or right path in the Y, or either of the straight paths. For example, if we want the robot to take the left path in the Y, we'll turn both switches off to get the number 0. Which will cause the first path to be chosen in the index, which is left. Once inside the while loop, we notice that the chosen path is being wired into a case structure, and determines which case will run throughout the loop. For now, we'll assume that the left case was chosen. In the left case, the steering gain control is being passed through, as well as the Y power, a number 4 labeled seconds, and a Boolean array of the 3 infrared sensor readings. For now, these values are just being passed through the case structure and are not being used. To understand what is happening each time this while loop runs, we'll begin by directing our attention to the bottom of the structure. A tick count is taken before the while loop begins, and is subtracted from the current tick count, providing the elapsed time since the while loop began, in milliseconds. Dividing this number by 1,000 gives us the elapsed time in seconds. A few things are done with the elapsed time. First of all, the program will exit this while loop if more than 8 seconds have elapsed since it began. Secondly, the power of the robot will be determined by how much time has elapsed, because the elapsed time is the index for the index array function that is connected to the Y power array. What this means is that the elapsed time will be rounded to the nearest integer, and that integer will determine which Y power is selected from the array, similar to how the path of the robot was chosen by the driver station switches. Therefore, at the start of the while loop, when 0 seconds have elapsed, the power of the robot will be negative 0.7. Whether this means that the robot moves forward or backward will depend on how the motors are mounted and wired. The third thing that the elapsed time will do is to check to see whether the robot is on the T at the end of the path, or at the split in the Y. To understand how it does this, we need to look at the second case structure. The outputs of the 3 infrared sensors will determine which cases run in this case structure. The default case is if the right and center infrared sensors are on the line, and so the Boolean array is converted to the number 3. Case 7 is if all 3 sensors are on the line, case 0 is if none of the sensors are on the line, and case 1 is if the right sensor is on the line. Notice that there are a total of 8 combinations that can be created using these sensors, therefore 4 of them are being ignored. And if the sensors are triggered in a combination that falls into one of these ignored cases, the default case will run, which is case 3. We'll begin by looking at the default case. In this case, the Y power is going directly to the Y-axis of the arcade drive function, so the power of the robot will be whatever the Y power was at that second. The value of the current case is wired into a feedback node, which we will discuss in case 7, where the value of the feedback node will be used. A false case is wired into the OR function that is connected to the loop condition terminal of the while loop, meaning the loop will not end in this case unless the elapsed time has exceeded 8 seconds. The only other value that is used in this case is the constant labeled left, which has a value of -1. There are 3 of these constants: right, straight, and left. In each case, one of them is wired into a multiplication function that the steering gain is also wired into. Recall that this was one of the controls on the front panel of this VI. The result of this multiplication function is wired into the x-axis of the arcade drive function. Therefore, the left constant, which has a value of -1, will cause the robot to turn in one direction, and right will cause it to turn in the other. This will again depend on how your motors are set up. Straight has a value of 0, therefore the robot will not turn at all. The degree of the turn will be determined by the value of the steering gain constant. A higher value will cause the robot to make a sharper turn, whereas a lower value will cause the robot to make a more gradual turn. To understand why the steering gain affects the robot's turning, think about how arcade drive works in teleop mode. The Y-axis, or pushing forward on the joystick, gives us speed, while the X-axis, or pushing right or left on the joystick, gives us steering. Keep that in mind when looking at the number being calculated and sent into the arcade drive function. The next case is the number 7 case. This case occurs when all 3 infrared sensors are over the line. There is a select function in this case, which will set the motor power to 0 if more than 4 seconds have elapsed, and set it to whatever Y power is at that second if less than 4 seconds have elapsed. the robot will drive straight, and its state will once again be passed into the feedback node. If more than 4 seconds have elapsed, a value of true will be sent to the loop condition terminal, thus ending the while loop. Otherwise, a value of false will be sent, and the loop will continue to run. The number 0 case is next, which occurs when none of the infrared sensors are over the line. In this case, the Y power goes directly to the Y-axis of the arcade drive, and a value of false is wired into the OR function. Therefore, the while loop will only end in this case if more than 8 seconds have elapsed. In this case, the feedback node takes the value of the case the robot was in previously, and puts it into another case structure which determines the way the robot should turn to get back on the line. The robot will continue turning in the same direction until it detects the line again. The last case, number 1, occurs only when the right sensor is on the line, and in this case the robot will drive straight. We assumed at the beginning of the video that the left case was chosen on the driver station, but the program behaves almost identically in the right and straight cases as well, with only a few minor changes. In the right case, the steering gain is reversed, and so are the infrared sensor readings. This is so that the robot tracks the right side of the line rather than the left. In the straight case, straight power is used instead of Y power for the motor power, and 2 seconds is used rather than 4 seconds to determine whether the robot is on the T or not. Hi there, welcome to First Team 2609's testing facility. We're going to give you a brief demonstration of the autonomous VI in action. Note that this demonstration was performed using white tape instead of black tape, and so the infrared sensors were wired up to send a true signal when they were in the false state, which meant that they detected the white line. Also note that the controls on the front panel were adjusted to optimize the autonomous code for this demonstration, and that each individual team should take the time to test the various values in these controls, and determine which one works best with their robot. That concludes the tutorial for the 2011 FRC autonomous code. Note that this program will only work if all the motors and sensors are hooked up to the robot correctly.